Hello, I'm John Doherty and welcome to another video in the series Nuts and Bolts of using PEST and PEST++. The subject of today's video is site sample files. Before we talk about the many uses of site sample files, let's just talk about their protocol. So a site sample file is an ASCII file, and it's a way in which you can store your field data, or as we'll talk about, it's a way in which model outputs can be stored. A site sample file can be prepared using a text editor, but it's probably most easily prepared through downloading from a database or a spreadsheet. It has 4 columns, as we can see. The first column has the name of a site. This has got to be 20 characters or less. This is also called a bore sample file in the old parlance, so this could be the name of a borehole. Site names, as I just said, are 20 characters and less. And all the data for one site must be juxtaposed with that for another site. You can't have them all intermixed. The second and third columns are dates and times. And it is also protocol for site sample files that these dates and times be in order of increasing time. The final column contains data. This can be field data, this can be model outputs. The columns themselves can be separated by space, tabs, or commas. Now, if you have prepared a site sample file and you want to make sure that none of these protocols are breached, you can run a little program that comes with the PEST Groundwater Utilities named SAMPCheck. SAMPCheck is run by typing its name at the screen prompt. If you run it, and if you don't have a file named settings.fig in the folder from which you run it, SAMPCheck will cease execution quite quickly with an error message. A settings file, settings.fig, need to have just one line, and it informs any program that runs it of the date protocol. That is, whether days precede months or months precede days in the entries of a site sample file. So, suppose that this file is in place, we can then run SAMPCheck. It asks for the name of the site sample file that it must check. It then reads that file and reports all errors that it finds, all breaches of protocol, to the screen. So why use a site sample file? Well, that's the subject of this video, and we'll show a number of good reasons. A lot of utilities from the PEST Groundwater Utility Suite read and produce site sample files. The tasks that these utilities perform are many and varied. They include processing, manipulation of model-generated and observed time series, formatting of site data for contouring and graphing, but mostly, and this is the big one, model post-processing and PEST input dataset construction. Construction of an input dataset for PEST++, where we have lots of observations, is time-consuming and error-prone. It needs to be automated. Programs that are discussed in this video will do that automation for you. So here's a quick example, and then we'll go into more details about this and other examples later in the video. Suppose I have a set of observations, field observations, and I have them stored in a site sample file. Let's just pretend that these are heads in observation boreholes. The coordinates of those boreholes will be stored in their own file. We'll show the protocol for that file shortly. And then I have a simulator. Let's pretend for the moment this is ModFlow. Now ModFlow and programs of the ModFlow family record their outcomes, their system states, in large binary files. I'm calling it case.hds in this case. In these binary files we have model calculated system states or dependent variables in every cell of the model domain. We may use a program called mod2samp, which we'll talk about more later in the video, to read that file and extract information from it that's pertinent to our observations. In particular, it undertakes spatial interpolation from all the heads that are contained in this modflow output file to the locations at which we have head measurements. Then we might run another program, samp to samp, which undertakes time interpolation to the times at which we have head measurements. This then comprises the model that is run by PEST, or part of the model. There'll normally be some pre-processing utilities run ahead of modflow which take care of parameters. We can then use a program, for example PEST prep, to build what I'm calling a partial PEST control file. This is that part of a PEST control file which takes care of all the observations, the observation data section, the observation group section. It lists the measured values of observations, the names of observations. It also writes a instruction file to read the model generated counterpart to field measured observations. All that's taken care of in this process. And then we can get more fancy. We can add more observations to the PEST control file, for example flow and budget terms. And as we'll talk about, we can engage in extra post-processing, for example time differencing, to supplement our observation data set. All this can be done using utility software that we'll discuss in this video, all based on usage of a site sample file. So that's a high-level overview. Now let's rewind, start with a simple workflow, demonstrate how it's done, and then get more complicated. So once again, here we have our field measurements. We'll continue to assume that we've got measured heads here, and that our observed heads from a set of boreholes are stored in a site sample file called heads_observed.smp. That our coordinates of those wells are stored in a file called wells.crd. Now let's assume for the moment, we're starting off simple, that we're working with a structured grid. Now modflow USG, modflow 6 can work with structured grids. It'll get a little bit more complicated as we go along. All of those models record system states in a binary file. We'll assume they're heads, but they can be other things as well, as we'll talk about. But at the moment we'll assume that these are heads and that the binary system state file or dependent variable file is called case.hds. We can run a program called mod2obs. This is as simple as the workflow can get. Mod2obs does both spatial and temporal interpolation at the same time. Mod2obs reads this binary heads file and interpolates the array of heads that it finds in that file to the sites and the times at which we have measurements. After it's done the spatial and temporal interpolation, it records the outputs of this dual interpolation process to its own site sample file, in this case called heads_model.smp. So this then is the model that's run by PEST. As we said before, there'll be some preprocessors in front of the model as well, but this takes care of the back end of the model that's run by PEST. As we'll see in a minute, we can then use another program, one of the PEST prep suite, to write a partial PEST control file in which all the observation data that figures in the inversion problem is listed, and in which an instruction file is read that can read the file that is written by mod2obs. Now if we're using modflow 6, we need to use a program mod2obs_dbl instead of mod2obs, because modflow 6 writes a double precision system state file. So let's have a look at mod2obs in a little more detail and then we'll run it. Mod2obs requires three types of file. It requires firstly a structured grid specification file. A lot of members of the PEST Groundwater Utility Suite read a structured grid specification file. This provides the number of rows and columns in the grid, but it also anchors that grid to the real world, providing the easting and the northing of the top left corner of that grid and the angle that the grid makes with the east-west axis. A structured grid specification file also provides cell, column and row widths. Now this is a very simple case where they're all uniform, but a structured grid specification file can easily accommodate more complicated cases where cell and column widths vary. The site coordinates file, or the bore coordinates file in the old terminology, simply contains 4 columns of data: the site name or well name, bore name, easting, northing and the layer number which the bore taps, and then the site data, the heads in each one of these wells. Suppose, in the example we're about to show, that these are named according to those green boxes. So let's run mod2obs. We run mod2obs by typing its name at the screen prompt. Immediately it asks for the name of the grid specification file, model.spc. After reading that file, it asks for the name of the bore coordinates file, the site coordinates file. wells.crd is the answer to that prompt. Now optionally, mod2obs can undertake temporal and spatial interpolation for a subset of the sites that feature in that site coordinates file. In this case we'll process all of them, so we provide the same name again when mod2obs asks for the name of a bore listing file. Next, mod2obs requests the name of the site sample file in which field measurements are stored, heads observed.smp. Then for the name of the binary dependent variable file written by a member of the modflow family from which we'll obtain arrays of model calculated heads. Case.heads is the answer to that question. Now mod2obs is an old program. In the old days it was able to read an MT3D output file which had a slightly different protocol. We're just reading modflow files. The answer to this next prompt is F. mod2obs needs to know how to identify a cell which is inactive in the modflow grid or which is dry. So we assume that we tell modflow, and it's easy to do, that if a cell is dry or inactive, then the dummy head value is above a certain threshold. That's how it's recognized. Here we inform mod2obs of that threshold. Next, mod2obs asks a few questions that allow it to relate simulation time to real world time. It asks for the time units used by the models, D for days, the starting date and time of the simulation, which we provide. It asks how many layers in the model so it can dimension its arrays. Now, if there's a measurement which precedes or postdates the simulation time, then mod2obs has to extrapolate. It asks how far is it allowed to extrapolate? We'll say 5 days. If we ask it to extrapolate any further than that, it'll tell us there's a problem here. Finally, it asks for the name of the site sample file which it has to write, which we provide. Then it does its job. So now, here are all our field measurements, and here is the model generated counterpart to these field measurements. Now we have the ability to build a PEST input dataset in which we can match apples with apples. Now when mod2obs is run as part of the model by PEST, obviously we can't answer all those keyboard prompts as it requests input from us. The responses to those prompts have to be put in a file, a text file, Let's assume that the name of that file is mod2obs_heads.in. Then we can run mod2obs using the command that we see here. We use this little arrow here to tell mod2obs, don't look to the keyboard for response, look to this file instead. So we run mod2obs, it does exactly what it did before. And here is mod2obs_heads.in. Just contains the answers we previously provided through the keyboard, but this time through this file. Now, let's suppose that we've got a pest control file. In this case, I'll suppose that I've got a partial pest control file written, for example, by TPL to PEST. TPL to PEST is a member of the PEST suite. It allows us to incorporate all our parameters into a pest control file, but not any observation data. So we're going to take this, we're going to assume that it's called start.pst as our starting point, and then add all observation data to this pest control file, writing a new pest control file in the first place. So you'll note that the observation group section of this file is empty, the observation data section of this file is empty. To fill those sections, we'll run pestprep2 by typing its name at the screen prompt. PestPrep2 asks for the name of the site sample file containing field measurements, which we provide. It asks for the name of the model-generated counterpart to that file. This is the file written by mod2obs. Now, in writing the new pest control file, it's got to name all the observations. It does this by taking the site name or the bore name and optionally adding a prefix to that name. And it also adds a suffix, which is the sequence number. Here we provide the name of the prefix, h underscore. It could, if we asked, give numbers to observations instead of names. We don't normally do that, so bore identifiers, site identifiers is what we request. If it has to shorten the site names to accommodate the prefix and the suffix, it asks whether it should take the first or last 15 characters. We take the first. What group should it assign the new observations to? An observation group called heads. What name should it give to the instruction file which it writes to read the mod2obs generated site sample file? Let's call that heads_model.ins. It writes that file. It asks for the existing pest control file, start.pst, and for the new pest control file which it will write, start_heads.pst, we'll call that. It then writes the file. And here's the file. It's got an observation group named heads in it, just as we asked for. Here are the observation names. At the center of each name is the name of each well, the site, a h underscore prefix, and a sequence number with for each site as the suffix. Here's our field data. In here, in the observation data section of the pest control file, read from the measurement site sample file, heads_observe.smp. Here's the instruction file which PestPrep2 wrote, and the model output file that it must read. That is the file written by mod2obs, run as part of the model. Let's have a look at that instruction file. It's a simple file. So now if we want to add more data, for example, suppose we want to add flux data to the PEST input dataset. We'll talk about how to do that later in the video. But we can simply add that data by running PestPrep2 again. Type its name at the screen prompt, provide the name of the site sample file containing field measurements, the name of the corresponding site sample file containing the model-generated counterpart to those field measurements, the prefix For the observation names, how to name those observations, just as before. The new observation group, the name of the instruction file which will read the model generated site sample file, the name of an existing pest control file, which is the one we just wrote, and the name of a new one, which is the one we'll write now. And here's the new pest control file. Flows, a new observation group, new observations, new observation values, new instruction file, new model output file. All we have to do is to get these weights right, and the PEST and PEST Groundwater Utility Suite provides a number of programs which allows us to formulate these weights in innovative ways. The only other thing to do is to create the model batch file and insert its name here in the model command line section of the pest control file. We'll look at this batch file later. So that's a simple mod to obs based workflow. Now let's look at how mod to obs does spatial and time interpolation. We'll start off simple. We'll assume we've got a structured grid. ModFlow, ModFlow USG, ModFlow 6 can all work with the structured grid. All of these programs record the outcomes of their calculation, their dependent variables, their system states, in a dependent variable file. These can be heads, concentrations, saturations, whatever. This file, as we've discussed, can be read by mod to obs or mod to obs DBL if it's reading a ModFlow 6 dependent variable file. If we run these programs, as we've seen, they ask for a structured grid specification file. This provides the specifications of the structured grid and also the location of that structured grid in the real world. Let's have a look at part of that structured grid. Suppose that we wish to interpolate to a well that's situated at where the red dot is. So mod to obs firstly finds the 4 model cell centers that surround that point. It then does linear interpolation along the top, linear interpolation along the bottom, and then linear interpolation in between. That's called bilinear interpolation. Now, it could have done things in the opposite order. It could have done vertical interpolation and then horizontal interpolation. The answer would have been the same. Mod to obs can of course calculate the fact that this grid can be orientated at an arbitrary angle to the east-west axis. Now let's suppose that we're using ModFlow USG and we're using an unstructured grid. ModFlow USG, like all members of the ModFlow family, records its dependent variables, its system states, in a large binary file at various time steps and stress periods that we choose that we want output at. This file can be read by USG mod to obs, another member of the mod to obs family. In order to undertake interpolation to a point in space, USG mod to obs reads a node to bore interpolation file. This can be prepared by a program called USG QuadFac, which is another member of the Groundwater Utility Suite. USG QuadFac obtains knowledge of the unstructured grid from which interpolation must take place by reading an unstructured grid specification file for the USG model, the ModFlow USG model. Specifications for this file are provided in PEST documentation. Now, this assumes use of USG QuadFac assumes that the grid is either structured or quadtree refined. So here is part of a quadtree refined grid. Now, the way in which interpolation is undertaken depends on where the bore or the well or the site to which interpolation is taking place It depends on where it is situated within this grid. In some cases, interpolation is simply bilinear, just as we talked about before. Bilinear interpolation is modified as we get close to parts of the grid that undergo quadtree refinement. Perhaps we only interpolate from 3 points instead of 4 in certain parts of that quadtree refined grid near the borders where we go from different levels of quadtree refinement. ModFlow USG or USG mod to obs that reads a ModFlow USG binary heads file can accommodate the fact that this grid is oriented at an arbitrary angle with respect to the east-west direction. And now let's look at ModFlow 6. ModFlow 6, if we use a dis or disv grid, then we can use a program called MF6 mod to obs to undertake spatial interpolation from that grid to an arbitrary point in space. So, just like other members of the ModFlow family, ModFlow 6 records a dependent variable file. MF6 mod to obs reads that file. To obtain the wherewithal to undertake spatial interpolation from cell centers of that file to an arbitrary point in space, MF6 mod to obs, like USG mod to obs, reads a node to bore interpolation file. But this time the file is written by a program called MF6 intfac. MF6 intfac is a member of the Groundwater Utility Suite. It obtains all the details of the grid from a binary file which is written by ModFlow 6 itself, called a ModFlow 6 binary grid file. So suppose that we have a grid, a disv grid that looks like the one pictured here. MF6 intfac locates the cells which surround the point to which we want to interpolate and form a triangle. It then does barycentric interpolation within that triangle from the cell centers which surround it to the point to which interpolation must take place. So that takes care of spatial interpolation. Time interpolation is particularly easy. It's just linear. So ModFlow or ModFlow USG or ModFlow 6 will record system states at the end of time steps and stress periods that are nominated in its input dataset. We can represent those by the black dots on this time axis. On the other hand, field measurements can be at arbitrary times, arbitrary dates, arbitrary times on those dates. So, time interpolation is, as I said, linear. We join these points at which we have model calculated system states and do linear interpolation to the times at which we have field measurements. We therefore have model generated counterparts to field measurements. So that's how members of the mod to obs family and other families which we'll talk about shortly do spatial and temporal interpolation from a model grid to points in space and points in time at which measurements have been made. Now we're going to get a little bit more complicated. We're going to look at mod to samp, bud to samp and samp to samp, where we actually separate spatial interpolation from temporal interpolation, which in some circumstances can be convenient. So as we've just been talking about, mod to obs undertakes both spatial and temporal interpolation, and in doing this it actually performs the role of two other programs, mod to samp and samp to samp. So here's mod to obs undertaking spatial and temporal interpolation, mod to samp undertakes just spatial interpolation, samp to samp undertakes time interpolation. Similarly, USG mod to obs replaces USG mod to samp plus samp to samp. MF6 mod to obs replaces MF6 mod to samp plus samp to samp. Each of these programs reads a modflow family generated dependent variable file, a binary file, and undertakes interpolation to the sites at which measurements have been made. Each of these programs writes a site sample file. Samp to samp then undertakes time interpolation from that site sample file to a site sample file which records the values of field measurements. Now, so far we've just been talking about spatial interpolation to the sites at which measurements have been made. And we've been talking about spatial interpolation of variables that the model calculates, system state variables. We can also, as mentioned previously, include flow terms in the inversion process. Here we don't really do spatial interpolation, rather we do flow accumulation. For example, what is the flow into this reach of a river or into this number of drain cells? A user has to nominate the cells in which flow is accumulated. If we're using modflow, then program bud to samp will read a cell-by-cell flow term file generated by modflow. It will record the outcomes of flow accumulation in a site sample file. Samp to samp will then do the time interpolation to the times at which flow measurements have been made. And by the way, those flow measurement times can be different for different sets of cells. If we're using modflow USG bud to samp reads the flow term file written by modflow USG. Samp to samp does the time interpolation. If we're using modflow 6, MF6 mod to samp accumulates flows in user prescribed cells, writes a site sample file. Samp to samp then does the time interpolation to the times at which measurements are made. So let's see how the workflow changes if we separating spatial interpolation or flow accumulation from time interpolation. Here's the previous workflow, and let's go back to assuming that we're interested in system states here to demonstrate this new workflow. So here's our measurements. Our site measurements are in let's pretend they're heads. They're in a file called heads.observe.smp, and as I just said, we can have field measurements made at different times, it doesn't matter. And our site coordinates in our in a file called wells.crd. And let's pretend we're using modflow and it's recording its system states, its dependent variables, in a binary dependent variable file called case.hds. Mod to samp reads the site coordinates file, undertakes spatial interpolation, and writes a site sample file in which spatially interpolated model outputs are recorded at every model output time, every time at which the model generates data that's recorded in case.hds. Samp to samp then reads the site sample file written by mod to samp, writes another site sample file containing the model generated counterparts to the measured heads. So this is the model run by PEST. And then, as we saw before, we can use a member of the PEST prep family to build a partial PEST control file. Let's see how this is done. We can run mod to samp by typing its name at the screen prompt. If we're working with a structured grid, mod to samp will ask for the name of the grid specification file. If we're using USG mod to samp or MF6 mod to samp, it asks for the name of a node to bore interpolation file. Once again, we have the option of just processing a subset of the wells of sites that are listed in the well coordinate file, in the bore coordinate file. Next, mod to samp asks for the name of the dependent variable file that it must read. These days we always answer F to this question. It's always a modflow file. Now it asks how many times are represented in this file. At this stage it's got to dimension its internal arrays, so we just have to provide a number here that's greater than the number of times at which modflow has produced output. Now if we don't know this, guess a high number, and in a moment we'll show how you can find out actually what's in a binary system state file recorded by a member of the modflow family. Mod2Samp needs to know how to recognize, once again, a dry or inactive cell, and we assume that these are denoted by very high values of heads. Once again, Mod2Samp needs to know how to relate simulation time to real time, so it asks the time units used by the model, and the model, the simulator, starting date and time. Next it asks for the name of the site sample file that it must write. We provide that name and it writes the file. Then we run Samp2Samp. Samp2Samp commences execution by asking for the name of the measurement site sample file. This is the file to which time interpolation takes place. It then asks for the name of the file that was just written by Mod2Samp. This is the file from which time interpolation will take place. It asks how many days prior to the beginning of the simulation time or at the end of the simulation time over which it's allowed to undertake time extrapolation. In this case we'll answer 5. Finally it asks for the name of the site sample file which it must write. We'll call that heads_model.smp. It then writes the file. Okay, so now let's have a look at the issue of how do you know what's in a binary file that a member of the modflow family writes. A binary system state file, a binary cell-by-cell flow file. So members of the modflow family record these giant binary files. They can contain dependent variables, they can contain cell-by-cell flow terms. They're large, they're binary, we don't know exactly what their contents are. We can find out their contents by using any of these 3 utilities. RDET stands for array details. For a structured grid model we'll use RDET. If we're using modflow USG, we can use USG RDET. If we're using modflow 6, we can use MF6 RDET. And it produces a table listing the contents of these files. See, each one of these files contains many arrays. Arrays of dependent variables, arrays of flow terms. Each one of these arrays is preceded by a header. These programs, these RDET programs, list the contents of these headers. And those headers tells you what's in the array that follows each header. So let's run RDET. We type its name at the screen prompt. It asks for the name of the grid specification file for the current structured grid model. If we're using USG RDET or MF6 RDET, it doesn't ask this question. It asks for the name of the unformatted, the binary file that it must read. This can be a dependent variable file or a cell-by-cell flow term file. In the old days, RDET asked, there was the option of reading an MT3D system state file. The answer to this question these days is always F. It then asks for the name of the file that it must write. It then writes the file, and here's an example of the file. These are just the headers that are found preceding each of the arrays in file case.hds, and here's the time step, stress period, the time, the layer to which each one of these, in this case, head arrays pertain. In other cases it might be a different system state variable. So now let's get a little more sophisticated. There are many occasions where we would like to include temporal differences in the inversion process. For example, if we're calibrating a transient model, It's often very important that we replicate the seasonal ups and downs of heads, because it may be important that the model that we calibrate is good at predicting those seasonal ups and downs. So we need to include the seasonal ups and downs or drawdowns in the inversion process. There's a program supplied with the groundwater utilities called SAMP-DIFF, which will read a site sample file and take differences. This site sample file can have field data, it can have model outputs. So SAMP-DIFF will read, for example, this file. And this file, as I said, can contain model generated or field data. And it can calculate, well, it can do things two ways. It can take differences between subsequent samples at every site, or it can take differences between each sample and the first sample for a particular site. In either case, it writes the outcomes of this differencing procedure in a new site sample file. So now let's see how we modify our previous workflow to include differences, time differences in an inversion process. Here's our previous workflow. So now the model run by PEST will be a little bit more sophisticated. Firstly, we take differences of the measured data. So here's our measured data recorded in this site sample file, and here are differences of measured data recorded in this site sample file. Every time the model runs, it now reads the model generated counterpart to our field data and undertakes differences. So this file and this file are equivalent to each other. This is the model generated counterpart to field measured differences. We then use PEST-PREP2, which reads the partial pest control file we had written before and adds to that partial pest control file a whole lot of new data incorporating those differences of system states. So let's run SAMP to SAMP. As usual, we run it by typing its name at the screen prompt. It asks for the name of an existing site sample file. Optionally, we can process only some sites within that file. So it asks for the name of a site listing file or bore listing file in the old terminology. Then asks for the name of the site sample file that it must write, and how differencing is undertaken, with sequential differencing with respect to the first measurement or model output value for each site, or with respect to a reference sample if we like. Should we retain the first sample from each site and transfer it to the output file? Optionally, we can do that if we like. It then writes the file. So here's our workflow, and this is the model run by PEST. Let's just have a look at this model. It'll be encapsulated in a batch file. So in this case, our simulator's mod flow. Here we're doing the spatial interpolation. Here we're doing time interpolation, and here we're doing the differencing. Now we can do this same workflow with any model really. To do this time interpolation and this differencing with another model, we simply take out this part of the batch file and replace it with the other simulator that we're using, and then we've got to provide our own programs which read the output files written by that simulator and undertake spatial interpolation to the sites where we have measurements. Once we've done that, everything else is the same. Let me just say another few words about site sample files before we move on to a slightly different topic and then finish this video. There's a whole lot of other programs supplied with the groundwater utilities which do a whole lot of other processing of information, of data contained in site sample files. Some of them are listed here. So for example, you could take the contents of a site sample file, interpolate them all to a certain date, and the data in the file that's produced can then be used for drawing piezometric contours over your study area. Another program will reformat the data so it's in plot-ready format. Statistics for each site can also be calculated. So just be aware that there's a lot of other things that you can do if your data is stored in site sample file format. Finally, let me talk a little about a program called OLPROC. OLPROC can be downloaded from the PEST web pages. OLPROC does a lot of what we talked about up until now, but also some extra things. OLPROC can read field data from site sample files or from CSV files, provided those CSV files adopt certain protocols. It can read model outputs from site sample files, but it can also read them from a ModFlow6 OBS package output file. So OLPROC can read data from all these types of files: field data, model generated data. And then it can perform a variety of complex functions. It can undertake time interpolation from model output times to the times at which field measurements of different types were made. It can undertake time differencing, just as we've been talking about. But it can also build much more complex functions of field data on the one hand and model outputs on the other, arbitrary functions based on the time series that were measured in the field or come from the model. And then it can match those so that these can become part of a PEST or PEST++ based inversion process. It records the outputs of this complicated processing in site sample files. And then it writes instruction files which can read those site sample files. And then it can build an entire PEST input dataset in which model outputs are matched to field data, differenced modeled outputs are matched to difference field data, and more complicated functions of model outputs are matched to the same functions of field data. So the inversion process then can become quite sophisticated. So OLPROC does two things. It runs as a model postprocessor in which all the complicated functions that I've just talked about are done. Every time the model is run, OLPROC runs behind the model, reads the field data, does the processing, and calculates the model calculated counterparts to processed field data. And then it can run as a PEST input dataset generator in which all this matching is incorporated into a complex inversion process. So everything is automated. Because the operations that it can perform are quite complicated, they're up to you how you want to formulate the inverse problem. OLPROC has to be provided with a type of script file in which it's told what to do. This is an example of a simple script file. It can be a lot more complicated than this if you like. To run OLPROC, we type its name, followed by the name of the script file, and then either a 0 or a 1. 0 if we wanted to build a complete PEST input dataset incorporating all the processing which I just talked about, or to run it simply as a model postprocessor, we replace that 0 with a 1. So this is the command that will appear in the batch file that PEST runs as the model, and then it just does the post-processing. Everything I've talked about in this video is documented in the manuals for the groundwater data utilities and for OLPROC. So in conclusion, what's decision support groundwater modeling all about? It's harvesting information from data, and this is done through history matching, when that information is extracted from the data and provided to model parameters which are adjusted through the history matching process. The information that we extract resides in raw field data, but also in differences, temporal differences, perhaps spatial differences, perhaps more complicated functions of the raw field data. We have to formulate the inversion process to extract that information by processing the field data, processing complementary model outputs, and then matching them during the inversion process. So, what we match has an important impact on whether and how we extract information from field data. So the history matching process must be complicated enough to do that. And the software which we've described in this video allows you to do many of the things that are necessary to extract information from field datasets and include them in a complex inversion process. History matching is then undertaken by PEST or PEST++, in which that information is extracted from the data to the parameters with which the model is endowed, adjusted to receive that information, and then when the model is used to make predictions, deliver that information to the decision-making process. That brings us to the end of this video. Thank you for watching.